Okay, hi everyone. First I would like to start with some general remarks. And we have a few people that ask me questions like what is, for example, how do you take the derivative of a function, what are partial derivatives? Maybe today there will be a few more of these concepts that you might not have heard of. Like, for example, I will talk about a vector space at some point. So that's you have quite a diverse background, so I'm trying to make the prerequisite relatively low, but some of the stuff I just require that if you have not heard that, then you just please look it up, and these are usually relatively simple concepts, like partial derivatives, for example. So just look up what is the concept and then try to use it and learn it as you go. There should not be too many of these concepts that are new to you. If that's the case, please let me know, but in general it should be okay, I've heard that a little bit, but that's slightly new kind of thing, and that's okay. Sometimes I just not explain every word that I will put on the blackboard. And then, if you don't know the word, just look it up if it interests you or if it's needed for your understanding. So that's, yeah, at the beginning of the lecture, the first few lectures, that will happen sometimes, that there will be new concepts for you and you have to look that up on your own. Okay, that's for the general remarks. Today we continue our study of surfaces. And actually the first part will be figuring out what is the correct definition of a surface. So that will be the first part of the lecture, and then the second part we will start with doing some calculus, if you want. How do you transport elements that you know from calculus, how to, for example, take derivatives as functions, and things like that. How do we make sense of that on a curved space like a surface? So that would be the second part for today. But I would like to start with just recalling from last time essentially where we stopped, namely that we had the definition of a parameterized curve. That was like the first part, which is essentially a function defined on some interval into R3. And similarly, we define parameterized surfaces, but instead of taking a subset of R, we take a subset of R2, and then require that this map is smooth, the same way that we require that map to be smooth. And then there were similar conditions that you could impose on a parameterized curve that has some kind of translation to the surfaces. One of them was, for example, that we talked about regularity of curves, that a curve is called regular if the tangent map is not, didn't vanish at every point. And similar, the concept that was translated to the surfaces, say that the partial derivative in x direction is not parallel to the partial derivative in y direction. These both are 2 points which are parameterized by points, and then two vectors parameterized by points, and we require them that they never parallel. And then they had that's essentially we call it for regularity for curves that what that ruled out was we didn't want it to have curves which looked like that, because here's kind of curves we didn't want. And you can imagine similarly that this kind of condition rules out that you have some kind of surfaces which go also like this, but then just like this, as surfaces. So we don't want these kind of things happening. So these are the conditions of regularity. And then there's something that we don't want self-intersections that we don't want for a curve. We don't want that they hit each other somewhere. And that was translated in requiring that this map is actually injective on the level of surfaces. So that was just a relatively straightforward idea that we can use from curves. We can take them over to the surfaces. But there's one problem, namely that parameterized surfaces, you can imagine them as essentially what I had said last time. You take a sheet of paper and you curl that a little bit, or you kind of deform that a little bit. So that's like a surface, and as long as you don't do that too strongly, that will be fitting a parameterized surface. The problem is that some surfaces that you would call surfaces are actually not fitting in these examples. So last time, for example, I asked you, what about, for example, the cylinder? Is the cylinder a parameterized surface according to that definition? Or maybe a different kind. What is about the sphere? You know the sphere, right? Just the round ball. That's definitely something that you would like to call a surface, right? It's two-dimensional, and it's as nice as you can imagine. It's nice round and should work. But what about can you find a parameterization of the sphere? Who found a parameterization of the sphere? I give that a little bit as a homework. Who thought about that and said okay, maybe I know the parameterization of the sphere. Yeah, so the standard example would be we just take polar coordinates, for example, right? So let's think about the example a little bit more. The most obvious parameterization is in polar coordinates by two angles. And I think couple of cosines and sines together. So what you can imagine is that like essentially you have one circle which is parameterized, say, by this cosine, like by this theta. It's just like one circle, and then you rotate that circle again around the axis to get like this sphere. So that looks like a nice parameterization, right? But remember, there was one important property, namely we have to talk about where it was defined. And this parameterization would be like obviously defined by saying that, for example, the angle satisfies this property, and then we have the other one has to until 2 pi. So these are like the definitions that require would give you the whole parameterization of the curve of the sphere. But there's a problem. Namely, last time I told you that we need this one to be open, so that we don't have like problems with derivatives. For example, if you like think about what happens if I want to like take this one and I glue that together, for example, then I get like a problem around these points. Like for example, this vector. If I look something like, for example, I can look all of the red ones look always like this, like it's a coordinate direction. So all of them look like this. But if I turn that around, then it means that at some point these vectors, like they point in like different directions or something like that, or just because they get identified around it. And we don't want that kind of problems, and that's why we need like require that this D is open. But open, I told you last time, means that we don't have like the strict inequalities here, but we need like a proper inequalities. So point here is that the largest open set would be actually where we have terms, but like here really without a so that's like defines the set D as like these two angles satisfying these two equations. So that's our set D that would be defined. But now we have a problem. If you look at this parameterization of D, we don't no longer get like the whole sphere, because now we removed like some angles here and here in this open set, and then we don't longer get the sphere. What you get is you have the sphere here. For example, what you don't get any longer is, I think, for example, phi is now always between 0 and 2 pi. So what never happens is that the sine of phi, or like that, this one is 0, for example, because like it's 0 and 2 pi, we don't insert it. I mean, 0 is out of that, but like for example, what never happens is that the sine theta is plus or minus 1, because plus or minus 1 means that sine of theta would be then part of these angles, which we just erased, because this one is now a strict inequality. So what we don't have is like the north and the south pole. These points are not included because we removed these angles, and then we removed also here like one angle, or like the boundary angles. And what that corresponds to, if you think about it for a second, it's like this small half circle. So we erased like 1/2 circle from the sphere. Let's call it here. So we don't get like a whole sphere anymore. But what we get is like the sphere except for this red part. So that's not really what we want. We want like the whole sphere. Let me record that. Image of this map psi, really seen as like a map from D to R Fourier. Only with the semicircle. Which is given by x0 and c. Now we have a parameterization, but it's no longer a parameterization of the whole sphere. It's like one semicircle is missing. And actually, it's a fact that we really see next time. There is no single parameterization of the sphere using an open subset. So that's something really worrying, because like we want to talk about like the sphere as an example of a nice surface that we want to talk about. But now this example shows you that you really can't like apply this definition of that I gave you last time of a parameterized surface. So that what this fact actually tells you is that if you have the sphere and you have like, for example, the sheet of paper, that if you try to put the sheet of paper around the sphere, that at some point, like for example, you get a kink or something like that. So that's not nice and round. So that's like if you try to do it, and like the paper always crumbles at some point if you try to put it around a sphere. So that's the expression of this statement. Like on the sphere, we can't find like a single parameterization that is defined in some open subset. So we have to think about, okay, okay then, maybe this idea or like this definition of like a parameterized surface is too rigid, because we want something that encompasses, for example, the sphere as an example. So we need to like find like a bigger concept, like a bit more flexible concept of the sphere, or like of the parameterized surface, or of the surface that includes these kind of like examples of that don't have like a single parameterization. And what we do essentially is like something that you maybe even learned in like your geography course. Like if you look at like all these nice cards that you have, like the atlas, and like you look at different kind of pictures from the Earth, it never shows you like the whole Earth, right? You never have like a picture of like the whole Earth, but it's usually just like tiny little bits on the Earth that like are interesting to you. And then you look at these kind of things, and then you know that, of course, like you can patch that together. Like you know that like there's some part of Asia, and then there are some other parts with an ocean there, and then like America comes. So you kind of have like a mental image of like how these things patch together. And we use the same kind of idea in mathematics, that we say we start with something where we kind of understand that part of it, and then we say like let's try to look at some other parts that maybe overlap a little bit, and then we glue everything together. So that's the idea of that we will use now, is that we glue things together in a nice way to get like the whole sphere. And the idea is that we want to say like, we start with the surface as something abstract, and then we say like each of like point in this abstract surface has some like the neighborhood around it that looks kind of like R2, like the plane that we know, or like a small piece out of the plane. So that's the idea, that every point has like some surrounding area where it looks like just like some piece of R2. The surface R2. Of course, that's not like a definition, so I have to make it precise what it means, like to be a piece of R2, what it means to like look alike. We need to talk about what piece means and what vicinity or like close to a point means. So these are like some things that I would like to make precise now. And maybe I do that on a new Blackboard. Essentially using these ideas that we had here. So to start with, given a subset, usually we consider that as like a subset of R3. Coordinate chart on S consists of. So we have a bit of a data to specify. First of all, an open subset of R2. So that, like the open subset is like, in this definition that I want to have here, is like, this will be a piece of R2. That will be this E. Then we need a non-degenerate injective and smooth map. Just which is defined on D, and which takes values in R3. And then an open subset which is living in R3. And you need to satisfy a property in here such that the image of this map is given by the intersection, which is just like all the points P. This one is given by the intersection of the surface with this open subset of O. And then we need like because it's like this phi is injective, we can restrict it to its image to get like an inverse. And this inverse, which is now defined on the subset, into D. It's continuous. Okay. So one of the ingredients I already told you to make connection. So we have this piece of R2 is just like our D. And then we have like vicinity of a point, essentially, in there. So a neighborhood. And that's essentially the subset. Which means like in some neighborhood, it looks like R2. So the picture here is that we have our S, and then we have our O, and then where they intersect, that's the intersection, which is S intersect with O. So that's this part is the vicinity of a point. So like say like there might be some fixed point in here. So that's the vicinity, and then we have to specify what it looks like. This part looking like is essentially given by these two properties that we have, namely that like this part that we have this map, which is like this part in R2 looks like this part on the surface. And then for essentially this one means that also like I can go back. That's the idea that like this part here gets mapped essentially to this part here. They are essentially both identified with each other. And we say that like a coordinate chart is centered at a point. Say like at a point M and S, if this point is mapped to 0, so if 0 is mapped to that point, so that means we have 0 here, we have a point M here. So this point 0 is mapped to M, then we see that this chart is centered at that point. So now we know, like that's like in some way it's like this mathematical definition of an atlas or like a chart in like geography. It's like saying like part of the Earth is described by certain coordinates, and that's like this idea that like you have the Earth, which is like this part of the picture, and part of that is described by just like some coordinates that you see in your map. So that's the definition of a coordinate chart, and now we can like say what a surface is, defining that, namely subset S. We got it in R3 called surface. Every point has a coordinate chart centered. So like small parts of the surface, that's the idea, small parts of the surface, not the whole surface, but only a small part of the surface is required to look essentially like a small part of the plane. And then we have some map that shows you essentially how this part of the plane is like changed. And then like you have this part, and then you might get like a different kind of map. For example, here you can think of, it's like a nice umbrella, because it has like essentially the coordinates depicted on it. So it's like, you can think of these ones like the black ones, for example, have the x direction, and the other ones have the y direction. And then this map here that tells you is essentially this like plotting the nice x and y coordinates grid that we have onto this like curved object, right? And like I can like choosing a different map, for example, I can like also deform that part and get like a different kind of surface. But also, I mean, I can also just take like some other map and put that one on there to get like some kind of different coordinate system. Like that's also okay. Like it doesn't have to be like part of that, like I described by some coordinates, and then I have like coordinates of a different part of the surface which have like different coordinates. So that's like one part of like that you sometimes have to decompose your surface into smaller parts where you get like nice coordinates. So for example, we can come back to our example of the sphere, which we showed that was not like a parametrized surface. Or maybe I should say that as already at the beginning, like every parametrized surface, like the definition that we had before, is of course a surface in this definition, where we only have one chart, when the chart is, coordinate chart is given directly by the parameterization. So if you have a nice parametrized surface, then that's also a surface in this definition. But like the nice part about this definition is that more examples are really a part of it. And one of them is the sphere. So what we could, for example, do is that we consider the following open subset, which is given by x, y, and c. Where c is like a strictly positive. So it's the upper part of the and then we have ft here given by x and y, where they require to be strictly smaller than 1. So that's part of like the definition of a coordinate chart. And now we need to define a map that maps like this D to the sphere. And essentially what you do is like you that's the part of, like essentially that's all, just like in 3 dimensions. So That's O. It's like the upper part of the sphere. And what we do is we just project it down. So if you have a point which is living here, what you do is you project it down. And that you can do everywhere, right? Like on this open subset, like if you consider the upper sphere, that defines like a map from this, like depending on your viewpoint, either from this map O going down or the other way around, that if you have a point here, you can like map upstairs to the sphere. So if you write that out in mathematics, is that like what you have is what you define is a map from x and y, which maps you to the point x and y, and then the z coordinates is chosen to be on the sphere, so it has to be 1 minus x squared minus y squared. And then let's check that this property is like fulfilled. Like first of all, we have to check that it's smooth, that you can just take by taking the derivatives. There's nothing problematic. We also have to say that it's injective, which is clear because you have two components which define already the point. So it's injective. What else do we have to check is that we have to essentially check this property that S intersected with the open subset is equal to the image of D. So yeah, like if you intersect the sphere with the open subset, what you get is essentially x, y, and z, such that x plus y squared plus c squared equals to 1, and c has to be strictly positive. And if you see, that's essentially, once you have these constraints, you can always solve this equation for c. So that's essentially what's happening here. So this one is, by definition, almost the same thing as the image of this map under the open subset of the points there. One more thing. We also have to check that it's non-degenerate, and let's do that. Non-degenerate is here. So we take the derivative in x direction, which would be 1, 0, and I'm too lazy actually. You can do that at home. Something here, and we take in y direction, we also get something here. And because these vectors have like 0, 1, and 1, 0, and 0, 1 here, they can never be parallel. So that means we check that they are non-degenerate. So that's defines you a chart. So that's maybe like the upshot of this discussion here is that this map phi is a coordinate chart on the sphere. So that's the upshot. But now, of course, you can repeat like the same idea and just use different kind of projections. For example, instead of the upper half sphere, you use the right half sphere and the left half and the lower one, and then you rotate it to have like the front and the back part. So if you add like, I think 5 more, so that you end up with 6 charts, then every point has like some neighborhood. Right, like here, like this chart is nice, it's like the upper neighborhood, but we, for example, we don't get essentially everything on the lower part, right? Like you don't get these circles here, and you don't get like the lower part. So if you do it then with the, for example, the next choice would be do it with the lower part, but then you don't get everything with these points, like the side points. So you need to also find like charts there. So you keep adding charts and charts and charts until you end up with like a complete collection of charts so that like everything is covered on your sphere. So the upshot is that the sphere is a surface, but it's not a parameterized surface. So that's the motivation for these different charts was like that we need like something that is more flexible than just using one parameterization to get like the covering of all of the surface. But actually, there's also a lot of flexibility now in there because we can, like as I showed with the umbrella, it's now possible to talk about having completely different coordinate systems that like overlap. So, for example, on the sphere, you know, there might be like these kind of coordinates might be very stupid actually to use for your problem, so, because they make like some kinds of problems like very hard because you have like a square root in there. So these coordinates might be very unhandy. What you might want to use are like different coordinates where you, for example, use stereographic projection. Where you map a certain point into the projection that you get from the North Pole, which is like called stereographic projection. That would be a different kind of like map that is like giving you a chart and coordinates on this upper half sphere or in the lower ones. So that's like gives you a different kind of coordinate system. And then we have seen also the polar coordinates at the very beginning that also give you some coordinates not on the whole of the sphere, but at least to a very big part of the sphere. And then you, for example, can rotate that to cover, like use the second chart to cover like the other half part and stuff like that. So there are ways to cover the sphere, but you always need at least two charts for that. And you have now different coordinates, and it's like possible to talk about, okay, how does it look like in one of the coordinates versus in to the other one. So we kind of lose like this rigidity of thinking that we have like one particular coordinate system that gives us all the information. But we can allow ourselves to say, okay, someone give me like some coordinate system that they prefer, and now I can calculate and like want to develop my theory independently of that. I really know that there is one particular coordinate system. And that gives you a lot of applications or like flexibility in applications because you can choose whatever coordinate system you want essentially to study the problems. So that's like the nice part about this definition is that we have now gained also a lot of flexibility and not just enlarged the class of examples that we look at. Okay. I want to give you another class of examples which are called ruled surfaces. And the prototype for that is essentially like the cylinder, for example. And what you can imagine the cylinder to be is that you have a certain curve. For example, we can like look at here this intersection between where it is, it's silver and white. So there's like a certain curve that goes once around the cylinder. And then we can think about that like we can have like a certain line, and then we rotate that line around that certain curve. So we have this line, and that moves around as kind of like is based on these points. So we have a line that moves around, and then as long as we do that, like it traces out the whole cylinder, right? Like the cylinder is something that is like straight in one direction and then curved in another direction. And these kind of examples are called rule surfaces. Which moves along a smooth curve. So the picture you should have in mind is that we have like our curve. At some point we have C of t, and then at that point you have a certain line, which is like parameterized by this vector L of t, which gives you the line. And then you can like move that around. So that's like if you now consider that as like the whole surface, that gives you a two-dimensional object, which is called a ruled surface. So you can think of that as something that is parameterized by the map, which has two parameters. One of them is you just like go in the direction of the curve. So you start essentially here, and what you then do is like, so that gives you one of the coordinates, and then the other one gives you that you move up a certain direction in the L direction. So what is, you can write this as L of t. So that's like like a parameterization, but it's again like a problematic for multiple things. For example, the cylinder is really nice because the cylinder is like in some way like there's a nice parameterization, but there's again the problem with the openness. The cylinder has like this 2 pi periodicity, so we need like t to be open. So actually we would need like this one to be of the open interval, and usually we need like this r needs to be small. The counter example would be, for example, if you have You have the circle, but now the lines are the lines which are like going down. And then at some point, they hit there. And then you don't get like a parametrization anymore, because parametrization was saying that you have every point has like exactly two ways to, has exactly one way to describe it. But this point I can reach in two different ways, right? Like I can start from this point and then move down, or I can start from this point and move down. So this point down here would have like two different coordinates. So this one would no longer be injective. So this one is not a parametrizational in the way that we described it before in the definition of a coordinate chart. So that's why I find like that the names that you use here is like a bit unfortunate. Not everything that is a ruled surface that is of this form, like for example, you can say like the cone would be something that is a ruled surface according to this definition because it has this description as a line, but it's not actually a surface in our definition because it has the singularity at the point. So this one is not a surface. At least if you include this point, like the vortex of the cylinder. So we don't want that, but like what you really need to think of if you say like a ruled surface is something that like looks locally